Good afternoon. We have the great honor to close our seminar season with Professor Keith Gubbins. Professor Gubbins started his academic career in the Department of Chemical Engineering at the University of Florida, where he co-authored the first text aimed at practical applications of statistical mechanics to fluids, particularly in chemical engineering. In 1998, he moved to the Department of Chemical and Biomolecular Engineering at North Carolina State University as the Double H. Clark Distinguished University Professor. Professor Gubbins is responsible for introducing statistical mechanics and molecular simulation methods to the chemical engineering community, demonstrating the superiority of Monte Carlo and molecular dynamics to the older macroscopic engineering approaches for physical properties behavior. This led to the becoming vital tools in the chemical engineering's repertoire. Amongst Professor Gubbins' most significant contributions is the development of SAFT. He was one of the first to realize and exploit the power of statistical mechanics treatment for the adsorption of gases and liquids in nanoporous materials. More recently, he has made major contributions to the characterization of more porous materials through the application of statistical mechanics methods and to understanding of diffusion process and chemical reactions in these materials. He has enthusiastically supported and guided countless research throughout their careers and inspired many young chemical engineering faculty. For these reasons, he is one of the most respected and warmly appreciated members of the molecular modeling community in chemical engineering. So once again, welcome Professor Keith Gubbins. Thank you so much for being here, and please feel free to start your talk.
Well, thank you very much. First of all, I'd like to congratulate you, the Atoms team, and particularly Fred Tavares for this seminar series. I've really enjoyed the seminars I've seen, and thank you very much for this nice invitation. So I'm going to talk about systems of 1 and 2 dimensions as opposed to 3 dimensions. This is a fairly old subject, but we became interested in this particularly because we believe that many inhomogeneous systems in absorption can be related to either 1 or 2 dimensional systems that are strictly 1 or 2 dimensions. So the practical systems were interesting.
Professor Gubbins?
Yes.
You need to share your screen again. Sorry, I didn't warn you, but
okay.
Your screen share stopped when we shared ours.
Just a second here. I think I have to maybe exit this to... can you see it now?
Yes.
Okay. Yeah. Just
can you
gotta enter presentation mode?
Yes, I'm going back.
Okay, it's perfect now.
Thank you.
Okay, so the work I'm going to describe is largely based on doctoral research of Matt Mansell and Kai-Heng Shi, who are shown here. They've both graduated now and have moved on. And the other collaborator is my colleague Eric Santizo, who we still work together quite a lot. And so I'll give some introduction, and then I will show results for thermodynamic properties and structure for 2 dimensions and 1 dimension, and I'll make some comments about unique features of those reduced dimensions and how they differ from 3-dimensional systems. And so part of our interest here is absorption, but we're also interested to know whether these quasi 1D and quasi 2D systems still conserve some of the unique properties of strictly 1D and 2D. And so 1D and 2D systems are easier to understand than 3D. We have very good equations of state for both 1D and 2D. In fact, for 1D, the equations of state are exact. You can solve the configuration integral for a one-dimensional system, and exactly, and this has been known since the early part or middle part of the 20th century. And finally, if I have time, I'll show some applications of these results for strictly 1 and 2D to some quasi-1D systems. So one thing we're interested in is what I call X-filled nanotubes. So you have, say, a carbon nanotube, you fill it with some molecules, you keep the diameter very small, so there's a very, very strong confinement effect, and the tube stabilizes a one-dimensional array of molecules. And you can see very interesting effects in this. There's not a lot of experiment yet, but you can see a transition from an insulator to a metal, for example, which may occur in the bulk, but only at very high pressure. You can see all sorts of semiconductor transitions, electronic properties are interesting, and so on. So we think of this 1 and 2D systems, the strictly 1D and strictly 2D, which is shown here in red. We think of them as reference systems for certain problems in thermodynamics and statistical mechanics. And so these are reference systems that we're all familiar with. The perfect gas, ideal mixture is one where the interactions between the different species of molecules are the same or almost the same. Infinitely dilute mixtures, we have Henry's law. And then we have other reference systems which are based on simple intermolecular potential functions like Leonard-Jones or Hart spheres. So for these strictly 1, 2, and 2D systems, I've listed some papers here where people have published an equation of state for the strictly 2D system. So there's this paper by Reddy and O'Shea. They covered densities up to 0.8 in reduced units. And this is a more recent paper by Kai-Hang Shi and collaborators where we extend this to much higher densities. So this is in the solid region. And we wanted to do this because in many of these absorbed systems, the density is very high. And so you may have a fluid in equilibrium with a porous material, but the actual absorbed phase may be solid in the case of materials like carbons. And this paper by Barker is for 1D systems, excuse me, and he solves the equations exactly. It's a very old paper, as you can see, but still very useful. And the interesting thing about Barker's paper is that he obtains an exact solution for a 1D system in an external field. And so we can think of our systems, our absorption systems, quasi-1D, but we can think of the porous material or the solid substrate or the nanotube, whatever it is, as exerting an external field on a quasi-one-dimensional line of molecules. So here are some examples of research areas where this may be useful. So I've mentioned absorbed layers, things like two-dimensional, so-called two-dimensional van der Waals materials. So graphene is the gold standard for this class of materials, but there are thousands of these materials now where you can prepare a material in as just a single atomically thick layer. And there are some van der Waals materials that are one-dimensional. So the classic example is gallium nitride. So in this case, the molecules have very strong bondings in a linear direction, which makes them want to line up in a straight line. So this is an image of these gallium nitride rods. Now, they're not a single line of gallium nitride molecules. There are several gallium nitride wires that are clustered together. And so if you think of a wire in the middle that's made up of gallium nitride, it's surrounded by other wires which exert a strong force on the central wire, and they stabilize it. So usually in these materials, they don't want to form a 2D or a 1D system that is freestanding. Usually you have to have some substrates or some external field that encourages them to form this geometry. Okay, so this is, before showing you results, I wanted to make some general remarks about, if we try to compare the behavior of 1 and 2D with 3D. So the essential feature of 2D and 1D is that the phase space is much smaller. Okay, so in 3D, we have three-dimensional material. This is, I think it's a body-centered cubic crystal. And so you have many possible quantum states. So Heisenberg tells us that, a quantum state in classical phase space corresponds to Planck's constant raised to the power of the number of dimensions and to the power of the number of particles. So when you go down to 2 dimensions, you have many less possible states. And when you go down to 1 dimension, you have only one axis, so you have less states. So roughly we can think that if we were in the microcanonical ensemble where the energy is constant, then there might be, say, lowercase n here of possible states, some very large number, but not infinite. And if we go to this case, for every one of these states in the one-dimensional system, we now have n states in this y direction. And we have a further power of n when we go to 3 dimensions. So very roughly, for a constant energy system, these numbers are in this ratio. And so if we now get the entropy, we use Boltzmann's formula, S is K times the log of the number of possible states, then we see immediately that the entropy is going to be greatly reduced when you go down to 2 dimensions, and even more when you go down to 1 dimension. And similarly, the configurational energy, because the coordination number is going down, and so in this crystal it's 12, but in this one it's only 6, and in this one it's only 2. So the configurational energy, which is generally negative, is going to be a much smaller number because of this smaller coordination number. So those two things combined, the reduction in the entropy and the reduction in the magnitude of the configurational energy, mean that, sorry, I'm going the wrong way. It means that the Helmholtz energy, A here, is the internal energy minus Ts. So if I go down to, say, 1 dimension, then this E is much less negative than it would be for 2D or 3D. So it's more positive, if you like. And the entropy is much smaller. So that means that A, the Helmholtz energy, at a given density and a given temperature, that Helmholtz energy in reduced dimensions is going to be larger, more positive than it would be for 3D. So the material is not going to want to form either 1D or 2D unless it has some very strong covalent bond in a certain direction that is so strong it overcomes this reduced entropy and reduced configurational energy. So gallium nitride is an example of that, and so is graphene. But even in those cases, you still need usually an external field to get the system to form 1 or 2 dimensional array. So some other features here are that the fluctuations in, say, the density or the fluctuation in the energy increases as you go down in number of dimensions. Now, it depends how you want to make this sort of comparison, but usually in many cases, it makes more sense to compare 3D, 2D, and 1D for a system of a certain length L. And so then you see that these fluctuations get larger. And this is going to be a major theme in what I'm about to show you, because the fluctuations drive a lot of the thermodynamics. In 3D and 2D, we can get phase transitions, as we know, but in 1D, if the intermolecular interactions are short range, so like Lennard-Jones, for example, if the range is shorter than 1 over r squared, you can show that you can't get phase transitions with those physically realistic potentials. But if you have an external field, it turns out you can get a phase transition. And so as you go down in dimensions, the spatial correlation range becomes longer. And this has an effect on particularly thermodynamic properties like the specific heat, the isothermal compressibility, Joule-Thomson coefficient, and so on. Okay, so let me first show you this phase diagram. So this is relatively old work, and the authors are shown here. So this is the temperature density diagram for three-dimensional Lennard-Jones. And so the points here are molecular simulations, actually taken from this Smith and Frankel paper. This is the critical point, and this is the triple point line. So this is gas, coexisting liquid, coexisting solid, and this is the liquid solid region. So as we all know, this critical point is at a temperature of 1.31 roughly. And this has been pretty accurately measured by Thanos Panagiotopoulos and other people. But if I go down to 2 dimensions, it looks like this. So now, because of the reduced phase space, the molecules have a much smaller coordination number, smaller entropy, and so on. They don't want to condense. And so you have to go down to lower temperatures to get them to condense. So this critical temperature is about 0.51. And notice this, this region near the critical point is very, very flat. So the critical exponent here is very different from this one. So this one, the critical exponent for this part of the coexistence curve is about 1/3. Here it's about 1/8. And then when we go down to 1 dimension, we don't have any phase change. Okay, so how do we compare 1, 2, and 3D? This is not an easy question to answer. There's not a single answer. How you do it depends on, you know, on what your particular interest is. So some remarks here. The critical temperature goes down as we go from 3D to 2D, goes down by a lot. But we also want to know about the critical density. So how do we compare 3D and 2D at corresponding densities? And the way that we have usually done this is not to look at rho star, that's rho times sigma cubed in 3D, or rho times sigma squared in 2D, but rather to look at rho, the density in the system of interest, divided by the close packed density. So if you think of a 3D system, the corresponding hard particle would be a hard sphere, and that has a well-defined close packed density. And in 2D, you have hard disks. In 1D, you have hard rods. So, so we're relating the density to the close packed density most of the time. Now, these second order derivative properties, these are properties where you take the thermodynamic potential, say the Helmholtz energy, and you differentiate it once with respect to, for example, temperature or volume, and that gives you a first derivative property. So in that case, those first derivatives would be the entropy and the pressure. And then if you take another derivative, a second derivative of the Helmholtz energy, you get properties like specific heats, compressibilities, thermal expansion coefficients, and so on. So this is what I mean by second order derivative properties. Now, these properties are very interesting. First of all, because you're taking a second derivative, those properties are very sensitive to small errors in the experiment, small errors in the theory that you use to predict those properties. Secondly, they are related through exact relations in statistical mechanics to fluctuations in things like the density, the composition, the energy, the enthalpy, and so on. And those relationships are exact. You're not making any assumption about classical statistical mechanics or pairwise additive forces or spherical molecules or anything like that. And so these are interesting properties, and they're driven by averages of these fluctuations. So if the fluctuations get larger, as they do when you go to 2D or 1D, you can expect that that will have an effect on these second derivative properties. Remember that density has a different definition in 2D or 1D. So density in 3D would be the number of molecules per unit volume. In 2D, it's the number per unit area, and so on. And similarly, the pressure has a different definition. So in 2D, the pressure is the force divided by the length. And in 1D, it's just the force. Okay, so so I'll show first some results for thermodynamic potential. So this is the Helmholtz energy, and I don't know how to get, it's gone. Okay, so at the top here, we have one-dimensional system. This is Leonard Jones at 3 different reduced temperatures, 1, 0.7, and 0.3. There are no phase changes because it's 1D. And so these curves show that the single phase is completely stable. If I go down to 2D, then the Helmholtz energy goes down. Still no phase changes because I'm above the critical temperature. This is 0.7 in temperature. Critical temperature is about 0.5. But when I go down to 3D, the Helmholtz energy is still lower. So this is telling me, first of all, that any given fixed density, say here, the 3D system is going to be equilibrium system. The molecules are not going to try to form 2D or 1D in a system that has no external field. These dashed lines are tie lines, so they're connecting coexisting gas with coexisting liquid. So all of this we could have surmised without doing any calculations. It's just confirming what we surmised in that table just now. Similarly, if I look at the entropy, I see that in 3D, we have a much higher entropy at a given temperature and density than I do in 2D, and 2D entropy is much higher than in 1D. And so, as we surmised, the entropy is much smaller in these systems of reduced dimensions. So now, those properties, this entropy is a first derivative property. It's given, this is the entropy, this is the equation relating it to A, the Helmholtz energy. So the Helmholtz energy is the thermodynamic potential for this canonical variables. And so it's saying that the system will reach its equilibrium point by minimizing the Helmholtz energy. It's the free energy. So now I want to go to the second order properties. And so these are the second derivative. If you think of canonical ensemble, it would be the second derivative of the Helmholtz energy. So if I take a first derivative property, such as the entropy, and I differentiate it with respect to the temperature, then I've got a second derivative property. And if I do that at constant volume, I get the heat capacity or specific heat at constant volume. So this ND, lowercase n here means the number of dimensions. So it could be 1, 2, or 3 in our case. So this specific heat is related to the second derivative, second temperature derivative of the free energy. And it's easy to show that this is given by this equation. So this is, if you're doing a simulation, this would be the ensemble average of the energy squared. And this is the ensemble average of the energy to the power 1. So this is the fluctuation, the mean squared deviation, if you like, of the energy. And if I do it at constant pressure, then I get this equation here. So this is now the instantaneous enthalpy, which you're averaging over a constant pressure ensemble. Here you're averaging over a constant volume ensemble, the canonical ensemble. So there are lots of these second derivative properties. There's a good treatment of second derivative properties in the book by John Rowlandson, Liquids and Liquid Mixtures, also in the book by the book on computer simulation by Allen and Tildesley. So I won't write all of them down, but there are dozens of these, and they all have some practical application. So here is the isothermal compressibility. So it's the fractional decrease in the volume when you increase the pressure isothermally. So you can also write it in terms of the density. And so this is the mean squared deviation in the volume. So you can, this is an important property. So we know that near a three-dimensional critical point, say the gas liquid critical point, close to that, the compressibility becomes very large because this mean squared deviation becomes very, very large. And this is driven by large fluctuations in the density of the system as it approaches the critical point. And so, as I'll show you in a moment, this isothermal compressibility diverges to infinity. Why is that interesting? Well, because we can make use of that in processes in chemical engineering like supercritical extraction. We want to operate near the critical point because of this high compressibility. So there are many more of these equations. There's also an isentropic compressibility, which has this almost the same equation, but here we're holding not the temperature constant, but we hold the entropy constant. So it's an adiabatic system. This is an important property to measure because it determines the thermodynamic speed of sound. And we can measure that speed of sound accurately. And we can use that to get other, to calculate other thermodynamic properties. Okay, so here we've talked about thermodynamics. Here's some structures. So these are just radial distribution functions. And this solid line shown here is for the one-dimensional Lennard-Jones. The dashed dot line is this line here. So that's 2D. And then the dashed line is this for the 3D fluid. So you can see for the 3D fluid, as we're used to, these oscillations are smaller and they very quickly die out. So this is a distance in terms of the number of molecular diameters. So by the time you get out to 5 or 6 molecular diameters in 3D, the oscillations have died out and the radial distribution function's gone to 1, which is saying there's no correlation over that after that range. But in 2D, it goes out quite a lot further. It goes out to maybe 10 molecular diameters. In 1D, it goes out even longer, beyond 14 molecular diameters. So here, these conditions are high density. We're not near a critical point. These are just normal, everyday fluctuations. So this is the longer range fluctuations that I was talking about in the beginning. This is showing molecular simulations of the mean squared deviation in the energy for 3D and 2D. You can see that in 2D, this mean squared deviation that determines the specific heat is about 2 orders of magnitude bigger than in 3D. And in 1D, it's even larger. I'll show you that in a moment. This is the corresponding mean squared deviation in the density. Again, about 2 orders of magnitude bigger in 2D than in 3D. Okay, so now I want to spend most of the rest of the time, last part, talking about one-dimensional systems. And I want to first mention some unique features. So the first thing, this has been known since 1940 or so, that in 1D, you can solve the configurational integral exactly. And so there are a lot of early workers like Van Hove and a man named Gersey, John Barker, Longuet Higgins, and others who published papers with solutions. So nearly all of the early papers assumed that the only interactions that mattered were the nearest neighbor interactions. So you have a central molecule and you say there's no interaction after the nearest neighbors. So in a linear molecule, there would be one nearest neighbor on the left and one on the right. So you'd have those two interactions. We rather like Barker's papers because he shows that you can solve exactly this configuration integral if you include all of the interactions. So not just nearest neighbors, but second nearest neighbors, third nearest neighbors, and so on. So he gets a nice exact equation. And the other nice thing about his paper is he includes an external field. So he was interested in, he had a theory of liquids called the tunnel theory. And probably none of the younger people have ever heard of that because it wasn't a very good theory, actually, it turned out. But at the time he introduced it, there were no simulations. It was 1960. And so he thought it might be a good model of liquids. And so he imagined this tunnel that had no molecules in it, surrounded by linear wires of molecules that exerted a field on any molecule that was in this central cylinder. So a good model if you want to model molecules in nanotubes, for example. And so because you can solve the configuration integral, you get an exact equation of state. But this equation of state contains a series of terms. And so the first term, the early terms would be the contribution from nearest neighbors, and the next term would be the contribution from next nearest neighbors, and so on. And if you go beyond 2 nearest neighbors, it gets computationally horrible. So we have used it with the number of nearest neighbor interactions included is 2. It's still tractable. Barker calls this lowercase m, this number. So we already made this point that because the entropy is very small in 1D, you don't get freestanding 1D systems generally. But if you have an external field of the right type, such as exerted by a carbon nanotube, then you can stabilize the 1D system. There are no phase transitions, provided the intermolecular forces, or intermolecular potentials, I should say, fall off with distance more rapidly than 1 divided by r squared. So you can't get any phase transitions in those systems. But if you have something like a CAC potential, which very long range, you of course can get phase transitions, but this is not a physically realistic potential. Left open is the question of whether there could be some sort of transition, even in a strictly 1D system, at 0 degrees Kelvin. And about 10 years ago, there was a couple of papers where people showed that there was a critical point in a one-dimensional Ising ferromagnet. So you might think there might be a critical point at 0 Kelvin in a fluid. because the one-dimensional fluid, because these are the same universality class. So as far as I know, nobody has proven that, but it seems to be a reasonable surmise, and I'm going to show you some results that suggest that there might indeed be some sort of continuous transition at 0 Kelvin. So these fluctuations get much larger on going from 3D, 2D to 1D, as we showed, and this has a big influence on the second derivative property. So first of all, here are some 1D results for the internal energy, which is the thermodynamic potential for an isentropic constant volume system. And so these points are molecular simulation, they're Monte Carlo points, and the lines are Barker's theory. So you can see that in these lines, which are isotherms, their agreement is very, very good until we get down to low temperature. And then you start to see some small deviations at temperature of 0.2, and 0.1 we see somewhat bigger deviations. This is coming from the fact that we took only nearest neighbors and second nearest neighbors into account. So although the forces with third nearest neighbors are very weak, that becomes significant if you go to very low temperatures. So you get some departures. So if you look at all these curves, they obey this condition. This is actually G, but a similar condition for U. This is the condition for a single phase to be stable. And so, as predicted, there are no phase transitions. But when you get down to 0.1, you see that this curve comes down almost on the axis here, where the pressure is 0, comes down very low pressure, and then it makes this very sharp turn where it becomes almost horizontal. So in a three-dimensional system, this would suggest that you may be approaching a transition where two phases separate. And you see the same sort of thing. This is the Gibbs energy or configurational part. Again, this condition is fulfilled, and so you don't have any phase separation, but you see again at this very low temperature, 0.1, you get this sharp bend. So this is a first order derivative property. It's the density. So we're doing these simulations in the isobaric ensemble. These are densities at different temperatures plotted versus the pressure. And these dashed lines are what you would get for a one-dimensional perfect gas. And again, you see this at very low temperature, you see this kind of a funny looking right ankle curve. So there's interesting things going on at low pressure and low temperature. So just because the pressure is low doesn't mean the density is low, because we're at very low temperature. So if you go to this very low temperature, this is showing you the low pressure region. This is the density. Then you can see that density stays around 0.9, very high density, until we get down to pressures approaching 10 to the minus 3. This is in reduced units, but this is, would normally at higher temperatures be a very low pressure. Okay, so this is the thermodynamic potential and one of the first order properties. These are now second order properties. So this is the heat capacity or specific heat at constant pressure in one dimension. So here is a high temperature, T star is 1. Then if I go down in temperature, then I start to see a maximum developed. So this is a temperature of 0.8, 0.7, 0.6. So now we're seeing this anomaly in the heat capacity as we go to lower temperatures. And notice the pressure is also getting lower. So if you look at 3D systems and you look at the heat capacity, it also behaves this way as we approach a critical point from above. And And so this is a big anomaly, and it blows up as we go to lower and lower temperatures. So here we're looking in the low temperature region. Here's the 0.6 that we saw here. Hard to see the maximum because we've compressed this scale of the specific heat. So now this is, as we go to low temperature 0.2, we're getting a really big anomaly in the specific heat, which looks very much the same as what you see in 3D near a critical point. The difference is this is occurring at, it looks like it's diverging at a very low temperature, would have to be 0 Kelvin because phase transitions are not allowed at finite temperatures. This is similar plots for this is the isothermal compressibility, is this equation here. And so this is a second derivative property also. And remember that fluctuation formula. So as we go down in temperature, this is 0.5, this is 0.4, 0.3, 0.2, and 0.1. So now at 0.1, this is diverging up to some enormously large number. And it's looking like it may go to infinity when the temperature goes to 0. So we couldn't explore yet lower temperatures than 0.1 because Barker's equation in the form we use it breaks down. You need these higher order terms that are very difficult to calculate. This is the lower temperatures for the isentropic compressibility. So this is the one that determines the speed of sound. And again, in 3 dimensions, you see this diverge when you get close to a critical point. When you're coming down in temperature from above the critical point, you see this divergence. So this is suggesting that there may be some sort of transition at 0 degrees Kelvin, as predicted by Lee and Kim. Lee and Kim were the group that showed that there was a transition at 0 Kelvin in the 1D ferromagnet. So some people may say, well, who cares about a transition at 0 Kelvin? It's not very useful. But I think it is useful because these fluctuations are so long range that you see major effects even when you're at much higher temperatures. Here we're seeing a divergence to a very high compressibility, even at T star of 0.5. So for argon, for example, this would be 60 degrees Kelvin, a long way above the absolute 0. This is just illustrating the fluctuations. So this is not near a critical point. It's not near temperature of 0. It's at 100 degrees Kelvin, 2,000 molecules, reasonably high pressure. And this is the configurational energy. So this is it's a NPT Monte Carlo run, quite a long one. And we're seeing, it just shows you how big the fluctuations are. These fluctuations about the mean, so the mean is somewhere here. We're seeing fluctuations of about plus or minus 7%. These are the radial, basically the radial distribution functions. They're actually H, which is the total correlation function, which is the radial distribution function minus 1. So these go to 0 at large separation distance. So this is the separation distance in units of sigma, the diameter or the length of the Lennard-Jones particle. So all of these are at the same pressure, pretty low pressure. So here we're at a high temperature. We're not near any transition at all. We just see this one peak, and then there's a very weak second peak, and then correlation's gone. But as I go down in temperature, these correlations get more and more long-ranged. Excuse me. So by the time I get to 0.2, we're seeing pretty strong correlations out to 20, 25 diameters. And when I get to 0.1, we're seeing these correlations still quite visible at 100 molecular diameters. So you're getting very large oscillations in the density as you go down to these low temperatures at fairly low pressures. So finally, I'm running out of time here. I wanted to show you that this can be useful in certain classes of problems, because we can map a quasi-ND system, say one of these are some examples here. So we're interested in the first two, absorbed films and absorption in nanotubes. But we're also somewhat interested in these 1D and 2D materials. They're not really 1D and 2D, they're called van der Waals materials because they're stabilized by neighboring either wires or flat surfaces that exert an external field. So we can think of ways to map this quasi-ND real system that's really 3D in reality, to map them onto either a strictly 2D or a strictly 1D. And this is useful because nearly always the problems we're interested in, we have a fluid or solid that's highly inhomogeneous. And then in that case, it gets very difficult to know how to define things like thermodynamic properties such as the density or the pressure, because these things are varying very rapidly with position. Whereas over here, we have a strictly homogeneous system. So the pressure and density are well defined. All of the thermodynamic properties are well defined. So one example is, this is the tangential pressure in a slit pore, which is made of carbon. So it's a pore width of 3 molecular diameters. It's the molecules in this pore are modeled on argon, and it's argon at its boiling point, 87.3 Kelvin. And so the normal way to calculate this would be to adopt a definition of the pressure. This is the Irving-Kirkwood definition, and calculate the average of the virial, the virial of force. And that, for this system, gives you these black circles. This axis is a measure of the wetting, how well the fluid or solid wets the surface. It's a molecular wetting parameter defined here. So these are the well depths for the absorbed molecules with the substrate or absorbed molecules with other absorbed molecules. So there's a competition between the forces with the substrate, say a carbon wall in this case, versus the interaction with other argon molecules inside the pore. This is where we've mapped the 3D system onto a 2D system, and now we can, we just have to calculate pressure in a homogeneous system. And so the agreement looks good. It's not maybe quite as good as you might think, because this is a logarithmic scale, but the same order of magnitude at least. So it might provide a way to calculate a more well-defined tangential pressure. The other example is Leonard-Jones argon confined in a single wall carbon nanotube. So here's the carbon nanotube. It's very narrow, but it's wide enough that it can let these argon molecules in. So they're not exactly one-dimensional. You can see here we've exaggerated a bit, that they're not all exactly situated on the axis, but there's quasi 1D. So now we can use Barker's equation of state, because we treat this nanotube as an external field. There are very good formulas for the external potential from a carbon nanotube or from a planar surface that people have worked out. William Steele did a lot of this, and that was followed by other people. So here is a comparison of the Barker equation with molecular simulation results. These points are the simulation result. You can see it's not perfect. So this is the density, this is the enthalpy, and this is the internal energy. And these are different diameters of the tubes, but all the tubes are pretty small diameters. So they vary from about just over 7 angstroms diameter up to about 8.5. And so the agreement on these properties, so these These two properties are thermodynamic potentials. This is a first order derivative, the density. Pretty good. More interesting are the second order properties. And so this is a heat capacity. This is at constant pressure or constant force. And again, the points are the simulations and the lines are Barker's equation of state. So now you can see that agreement is not so good. There's some vague qualitative description of what goes on, but it's far from quantitative because now we're taking second derivative. So, you know, Barker's equation's not completely accurate. So the real behavior is given, we think, by these simulation results. So here we start to see a small anomaly. This is at a very high temperature of 372. So we don't expect any significant anomaly. But as I go down in temperature, we start to see this anomaly. So this is the lowest temperature is 60 degrees Kelvin. And we see a peak here, just like we did in the freestanding strictly 1D system. And we see that same peak here and over here. And we also see divergence. This is the thermal expansion coefficient. So this is the formula. It's again given by a fluctuation, a local fluctuation, and we're seeing divergence as we go down in temperature. This is 60 degrees Kelvin, and the same for the isothermal compressibility. We're seeing divergence. So these unique features of the strictly 1D system are still observable in these confined systems where you have the system in a carbon nanotube. Finally, this is the structure. Well, as you expect, as you go down to lower temperatures, the blue lines are the lowest temperature. These become more long-ranged, and so we're increasing the pressure here as we go down to these different results. So as we lower the temperature, we increase the pressure, we see longer and longer range oscillations. This is the total correlation function. So I'm out of time here, but this is a summary of what we think about this, that strictly 2D is a very useful reference for things like absorbed layers. 2D arrays are used in DNA technology. It may be useful there. 1D is a useful reference for things like one-dimensional van der Waals materials and our interest, which has been so far in these X-filled nanotubes. And then this is, certainly we have not proven this, but there appears to be signs of a singularity at 0 degrees Kelvin in the 1D, in the quasi-1D systems and in the strictly 1D systems. And this leads to divergences in the thermal properties that are second derivatives of the Helmholtz energy. And this may have some practical application. You lower the temperature, don't have to go terribly low, and you see these divergences. So if this is in fact a continuous transition at 0 Kelvin, then you can adjust just by adjusting the temperature and pressure in a quasi-1D system. You can obtain extremely large specific heats, extremely large compressibilities, and similarly large values of Joule-Thomson coefficients and other second derivative properties. Not all of the second derivative properties diverge as you go to a critical point. So there's one or two that don't, but many of them do diverge. And these divergences in the 1D systems are visible at much higher temperatures than far above any possible critical point at 0 Kelvin. So it doesn't require, it suggests that you can obtain very high values of these second derivative properties just by adjusting the temperature and pressure. And it doesn't depend very much on the intermolecular forces. It's coming from these long-range correlations. So whether you use argon or benzene or something else, shouldn't have much effect on these divergences. So you're not restricted by the intermolecular forces if you want to get a very, very high heat capacity in some nanoscale system. Well, I'm certainly out of time, and I thank you very much for your attention and for the invitation. And I'll certainly try to answer any questions if I can. Thank you.
Thank you.
Thank you, Professor Gubbins, for your amazing presentation. We are really glad to have you. So now we are open for questions. If you want to ask, you can raise your hand or write down on the chat here at the Zoom or on our YouTube. Please feel free to ask.
Let us start. Thank you, Gub, for this very nice presentation. I wonder, one point is how to include electrostatic interactions, not come from external field, but rather from the component that make 1D. So is it possible if you take in account M equal 1, 2, 3, and include electrostatic? So it means long range interaction in this?
Yes. Are you thinking of an external electric field that would be applied
No.
by putting a voltage, or just coming from the molecules?
From the molecule.
Yeah, that's a good question. I don't know the answer, Fred, but it's certainly something to think about. I mean, you can think of various other ways to apply an external field. In the example I was showing, it's just coming from the strong interactions from the surface of the carbon in the nanotube.
Because well, we have trouble in put together long range and short range. Maybe if you could in a correct way put these together in 1D, so it can help to think about other system like 2 or 3D. I don't know.
Yes. Yeah, I mean, this is a very new field, I think, and on the experimental side, there have been very interesting experiments by Katsumi Kaneko in Nagano, and he studied sulfur and also selenium. So he was studying group 6 elements, and he saw a number of interesting effects. He saw, unique structures, and he observes this transition from an insulator, which sulfur is normally an insulator, to a metal. He measured the electrical conductivity of the nanotube with the sulfur inside, and then further experiments were done. Excuse me, a group at Cambridge, Medeiros et al., who studied tellurium and saw the same thing, and they also saw a transition from insulator to semiconductor. So it turns out in their experiments, they had very good control over the diameter of the nanotubes. And so they were able to slowly reduce the diameter. And as they did so, they saw a series of phase transitions. There are lots of experiments on linear arrays in carbon nanotubes where people see, what they call topical electronic states. So this is quantum confinement, quantum confinement of the electrons. They're interested in electronics. But we couldn't find anyone that had looked at simple thermodynamics. And so all of these early papers on 1D, the people were all mathematical physicists. They derive an equation, and that's that. They don't do any calculations. And
Let me ask the second question. in 2D or quasi 2D, if you put external field, you may present a second critical point. You see this kind of
not aware of that.
We saw that in very simple model. Use confinement. The confinement may gives you the second critical point.
Yes.
So I wonder if you, with better model for 2D, you can understand better, because in my case was very simple model. So I'm more about this. But with a better model for 2D, with external field that we can take in account, maybe you could see the second critical point. But now with better model, you can understand better. You know?
That would be very interesting to study. I'm not aware. I mean, there may have been, but I haven't, looked for the literature. But I haven't, noticed papers on that. That would be an interesting thing to study. And also, there's all this work by Pablo Di Benedetti and co-workers on this metastable low temperature critical point for water. So
yes.
I suppose still controversial, but they see it, very clearly in molecular simulations.
Well, even in perturbation theory, if you put a showed potential, you can see the second critical point. But the problem is the second critical point is in a non-stable condition, like is inside the envelope for solid phase. So we do see, but it's not a stable second critical point. I think the same is for water. But the interesting that you can see kind of stable second critical point if you take in account the external field in 2D or confined fluids.
I see. Yeah, that's very interesting.
Thanks, Gub.
Okay, you're welcome.
Thank you. Now we have Professor Richard. You can go.
Hi, Keith. It's Richard Elliott.
Oh, so, Richard, hi.
So I didn't hear anything about like an Ornstein-Zernike approach to any of this, like some closure and that kind of thing. I was wondering, is that because it's too complicated? I vaguely recall you had to use Bessel functions for a 2D Fourier transform or something.
Yeah, I think people have looked at that. In fact, in John Barker's 1961 paper, he has a section on integral equation, an integral equation form of his theory, and he solves it. But he doesn't do calculations for some reason. He just gives the equations, and we haven't used those particular equations, but we should actually, because we should be able to calculate G of R in the same approximation as we calculate thermodynamic properties. Yeah, there are probably I'm sure there are other papers where people use integral equation theory. So integral equation forms, I mean, of the theory.
Okay, thank you.
Thank you, Professor Chapman. It's your turn.
Thank you very much, Keith. Fantastic talk. I recall when I was a first-year graduate student at Cornell, and you gave a short talk on your research. I thought, oh no, now everyone is going to want to work with Keith. Of course, I was lucky enough to be able to work with you. So what I'm interested in is, I know you've also done work on transport properties in 1D or pseudo 1D materials. And I wondered if you could comment on any relationship between the thermodynamics that you're seeing and the transport behavior.
Well, one thing that I think would be interesting to do, and I don't have a student or postdoc to do this at the moment, but one thing would be interesting to look at the thermodynamic the transport properties in 1D as you go towards low temperature, because in 3D, as you know, we see these divergences for the second order thermal properties as we go towards the critical point. But we also see, but in both experiments and theory, these divergences in thermal conductivity and viscosity. And a lot of nice experimental work was done by Jan Sengers and co-workers on this, and also theoretical work, but only in 3D. So these divergences for transport, I would expect, would exist for, thermal conductivity and other transport properties, electrical conductivity, I would expect. Mm-hmm. So this would certainly be one thing of interest in transport properties. There may be other things. I mean, we didn't, when we started this work on thermodynamics in 1D, we didn't expect to see divergences. We knew that there were no phase transitions, and so there was no reason to expect divergences. But so, who knows what would happen with transport? That would clearly be an important thing to study.
Certainly. Yeah. Thank you very much, Keith. Yeah, fantastic talk again.
Thank you. Thank you, Walter.
You can go now, Professor Raj.
Thank you, Professor Gubbins. I'm so happy to be associated with you many years ago. I just want a clarification from you along the lines Chapman mentioned, especially in lipid bilayers. You mentioned about protein lipid bilayers. There is one-dimensional transport. First, the swelling happens. You think there will be anything like inside is different from outside? There will be anisotropic effects because of the anomaly? Transform from inside to out, not outside to in, for example.
Yeah, I haven't worked on that or even read a lot about it. But I would expect there would be, signatures of 2D effects, the sort of things I described in the thermodynamics.
How important will be this anisotropy in these bilayers? The equilibrium, for example, we put a sugar outside and it causes a swelling and it goes in and out, the out comes ions. Various things you read about, they're all mysterious.
Yeah, these are bilayers, right?
Yes.
Two planar layers. I would think the, inhomogeneity would be very important. Things like the stress, for example, or the pressure, which is minus the stress, would depend very much on position. Just as we see, in absorption systems, we see this. That these pressures vary by orders of magnitude as you move around in this nanoscale system. So, so then that makes the system hard to deal with, hard to define what you mean by pressure and density. But if you could map it onto a strictly 2D layer or two strictly 2D layers in contact, if there's no interaction between the layers, then the layers themselves would be homogeneous. Everything is well defined, the pressure, the density, and so on. There's a definite average of those in statistical mechanics. So, I would think that would be a pretty promising way to go about the problem. To study the real lipid bilayers, but I haven't tried it. I haven't worked in that area myself.
Thank you, Professor.
You can go, Professor Richard.
Oh, okay. Thank you. I want to ask one more question. It may be a very stupid or naive question. But it starts with, what's the definition of temperature in these systems? Is it just the kinetic energy again?
Yes. Yes, I mean it's the average of the kinetic ensemble average of the kinetic energy. So now that's a half half mv squared in one dimension.
Okay.
So
So
you could define a new scale of temperature, but
so here's the thing that bothers me. So imagine you've got a system where you've got a two-dimensional surface and then a three-dimensional fluid in equilibrium with that two-dimensional surface. And there's a field that causes the adsorption, right?
right.
So as the molecules are at a certain kinetic energy in the vapor, then they attract, they're moving towards this surface and they become confined at 2D. So there's some on the surface wandering around in 2D. And just before they're in that surface, they're in 3D. So, they're attracted to the surface because of the field. If they're attracted to the surface, their kinetic energy is going to increase. And so, but then in 2D, it's what it is. So if their kinetic energy is continuously varying and you're going at some arbitrary point from calling it a 3D system to a 2D system, how is your definition of temperature evolving?
Yeah, that's it. I mean, we don't go about it in that way, actually. We have the same definition of reduced temperature as when we do the comparisons, but you could redefine the temperature scale, as you say, in 2D. And that might be an interesting thing to do. We haven't actually done that, but but yeah, I would need to think about that, I think.
Okay, it's just been bothering me. Okay, yeah, I just wondered if you knew, I thought if anybody knew, you'd be the guy.
Well, we've talked about it, but we haven't really done it. But the temperature, I mean, in practice, the temperature in Kelvin is the same, excuse me, in the 3D gas phase, for example, that is a bulk phase that's in contact with the solid substrate, then that temperature in real units is the same, right? And unless you want to redefine a new scale.
Well, yeah, I guess it's just I don't know. I'm probably beating a dead horse, but it's the kinetic energy. I understand that definition, and it's just how do you make the connection when you suddenly transition?
Well, the overall system is 3D, and you're looking at a part of a 3D system that is on the surface.
Okay. So you apply the three-dimensional definition. So the way I remember the definition is you just divide by the number of dimensions, right? So if it's a 3D system, you divide the kinetic energy by 3. If it's 2, you divide by 2. So would you use the three-dimensional definition of temperature for the molecules that are on that two-dimensional surface?
Well, I think that.
Would you divide by 3? I guess that's the question.
I mean, if you regard the absorbed monolayer, excuse me, as a two-dimensional film or quasi two dimensions, then by equipartition, you have 2 dimensions, each of which is a half kT on average, average of the kinetic energy, and so I don't think the definition of temperature is really changed, but you just have less, you have less average kinetic energy. Does that make sense?
I don't know. Not well. So so for those molecules that are confined to the surface, we divide the kinetic energy by 2. Is that right? Is that what you said?
Well, if you say the surface is the XY plane, then you'd have a half kT in the X direction and a half kT on average in the Y direction for the kinetic energy, right?
Right. So you divide by 2 on the surface, but 3 some arbitrary distance away from the surface.
Well, now you don't have a 2-dimensional system anymore. It's 3-dimensional. So now you have, you know, an extra half kT kinetic energy, which corresponds to the direction normal to the surface.
Okay. But those molecules have the same velocities, whether they're, you know, 0.001 nanometers or 0.002 nanometers or, you know, wherever they go. So there's some sort of discontinuity then when you change from dividing by 2 to dividing by 3.
I don't think so. I mean, the velocity distribution in 3D would be given by Maxwell-Boltzmann, and it would also be given by Maxwell-Boltzmann in 2D, but, you know, now you have one less dimension if it's strictly 2D, and so the distribution, you know, of the velocities Vx in the X direction would still be given by Maxwell-Boltzmann, at least classically, and similarly for the Y direction.
Okay, I must be thinking about it. I need to rethink how I'm thinking about it. Okay, thanks. I'm sorry to take up so much of your time.
Oh,
No, it's nice talk. Nice discussion. I like.
So we have one more question. Naef, you can ask now.
Thank you very much. Thank you, Professor, for your presentation. It's related to the maximum in the specific heat and isothermal compressibility. We know a point where we have the Widom line, and it's supposed to be located on the same line. Does this apply for the second order in Lennard-Jones? Does this, you know, represent the Widom line? And the second part, and when we try always to test, you know, the Lennard-Jones, they never satisfied the second order maximum as the Widom line above the critical point.
I'm not sure. I haven't thought about that, but it's a good question. I would think that, you know, the Widom line would still, you know, give a second order term that would be consistent. I would need to do some reading and think more about that.
Thank you.
Okay, so thank you all. I think it's time to wrap it up, right?
Yes.
So I would like to thank again Professor Gibbs for joining us in this series of seminars. It was a pleasure to have you here in our seminars, and thank you again.
Oh, thank you all atoms.